Hello again. So our next installment is the extraction of calcium carbonate. And I thought this time there's quite a bit of calculations involved with this, but I thought we'd go through firstly the method and with that why we're doing certain parts of the method, any issues that we could have with that method, and also any improvements then that we could do. Okay. So obviously starting off, we're weighing out the marble chips. We're then placing the chips in a beaker and then adding the 2 molar HCl. Okay, then with the stirring rod, we're going to heat it gently until they've all dissolved. Now, one of the things that we will be looking at when we're actually dissolving the calcium carbonate in hydrochloric acid, calcium carbonate isn't really soluble in water, and of course we react it with hydrogen, with HCl, sorry, so that it will dissolve. And when you do this practical, sometimes we don't always get everything dissolving straight away. We're heating it gently. It says until all the chips have dissolved, and this can take some time depending as well on the size of the marble chips. So an issue there, we're doing that stage number 3 to get the marble to dissolve. An issue with that is that potentially it takes a long time and some particles are left over, which we have to filter. So an improvement for that, instead of using chips, I guess we could use maybe a powdered form instead. Larger surface area, it'll react a lot easier with the HCl. So there's a thought there. Then we're going to be adding our sodium carbonate to the solution after we've filtered it. And basically it's a displacement reaction that we're getting here. So the sodium is going to displace the calcium and reform calcium carbonate. Now, again, when we're doing this, it's saying a precipitate will form. We heat the solution by boiling to fully precipitate. Now, do we know, we're doing that so we can precipitate, but do we know that we've fully precipitated all of the calcium carbonate? At that stage, we don't. We're just following the method. So again, an issue there could be that we've not fully precipitated. So how could we potentially do this, to improve it? It could be a case of once we filter the solution to get the precipitate, the resulting liquid that we get there, we could then maybe look at adding some more sodium carbonate to that to see if we get any further precipitation. And if we do, then obviously we can filter that again and extract some more of the calcium carbonate. Next one is, if we look at number 8, washing the precipitate. So we've done hot filtration using the Buchner filtration system. And again, I mentioned calcium carbonate isn't really soluble, but it is partially soluble in water. So again, if we're going to wash some of that precipitate with distilled water, we're cleaning it, trying to remove any other impurities. But in the process, we could potentially wash away some of the calcium carbonate there. And then we then give it a wash with ethanol. It's not soluble in ethanol. And we're allowing it then to air dry. This will help, the ethanol will help get rid of residual moisture that's within the precipitate as well. So again, looking at how we could do this is something like, if we're going to use distilled water, maybe we use cold distilled water. Okay, because obviously as temperature drops, solubility decreases even more. So again, that's just something to think about. Okay, moving on. So we're looking at, I gave you a set of results. We started off with 8.03 grams of marble chips, and at the end of this method, we had 7.4 grams of calcium carbonate. So just turning over. So determining percentage yield. Okay, so it was the mass extracted divided by mass of the original sample times by 100. And again, just using those two masses from the previous page, 7.46 divided by 8.03 times it by 100. That should give 92.9%. Okay, so a relatively high yield there. Pat yourselves on the back. But now we need to determine how pure that sample is. Okay, it's a white powder. Is it 100% calcium carbonate? And of course, we will use the data that I gave you for a titration. And this type of titration, we call it a back titration. We use an excess of acid with the calcium carbonate. And we actually determine how much acid is left over, and from there we can work out how much acid did react with the calcium carbonate, and hence we can work out how much calcium carbonate was in that sample, and from there we can work out a purity. Okay, so again, I gave you details of the different masses of calcium carbonate that we used, and this titration was done 4 times. We had the rough one and then 1, 2, 3, and of course when we're doing a titration we want to have a minimum of 2 concordant results, and with the actual volume recorded, in fact the rough one and number 3 were concordant results at 30.10 centimeters cubed. So they're the 2 bits that I'm going to use, and I'm going to use the 2 corresponding masses as well. So if we turn over, we're given the reactions that occur, but before I come into that, we're just going to do number 1 here. So we have to calculate the average mass. So the 2 masses I'm using are from this one and this one. So we add them together, divide by 2, and that gives us 0.1267 grams. And of course, we're going to be using this titer and this titer result. So it's 30.10 plus 30.10 divided by 2, of course, gives us 30.10. We then need to calculate the volume of sodium hydroxide used, because of course this titer value is of the volume of sodium hydroxide that was used in the burette. So again, very easy to convert. Centimeters cubed to decimeters cubed, divide by 1000. So 30.10 divided by 1000 give us 0.0301 decimeters cubed. Working out moles, N equals C times V. The concentration of sodium hydroxide used is 0.1. So times that by the volume, which we've already calculated, 0.0301, and that will give us 3.01 times 10 to the minus 3 moles. Then it's asking work out how many moles of HCl have been neutralized. Look back at the formulas that we've got, the chemical equation, for the neutralization, and we can see that sodium hydroxide, hydrochloric acid, it's a 1-to-1 molar ratio. Okay, so therefore we can say moles of sodium hydroxide equal moles of hydrochloric acid. So I've said there, so then moles of hydrochloric acid equals 3.01 times 10 to minus 3, the same that we calculated for the sodium hydroxide. Next we need to work out the amount of HCl that has reacted with calcium carbonate. Okay, and this is a volume. So we know how many moles we have here. We can work that out as a volume. Okay, so using the equation N equals C times V, rearrange that. So V equals N over C. We've got the volume. The concentration of HCl used for the titration was 0.1. So 3.01 times 10 to the minus 3 divided by 0.1, equals 0.0301 decimeters cubed. I've converted it back to centimeters cubed by timesing by 1000. So that tells us that 30.1 centimeters cubed of hydrochloric acid had reacted. We started, if we look back at the method, we started with 50 centimeters cubed of hydrochloric acid. So to know how much had reacted with the calcium carbonate, we do 50 minus 30.1, which will give us 19.9 centimetres cubed of hydrochloric acid that's reacted with calcium carbonate. Then the next step is asking us to work out how many moles of calcium carbonate have reacted. So first thing we need to do is work out how many moles of hydrochloric acid had reacted. So the concentration being 0.1, we're using N equals C times V. So it's 0.1 times 19.9, divided it by 1,000 because this was in centimetres cubed. And that gives us 1.99 times 10 to the minus 3 moles of HCl. Looking back at the reaction, so the molar ratio calcium carbonate to hydrochloric acid is 1 to 2. So if we know how many moles we've got of HCl, to work out moles of calcium carbonate, we have to divide moles of HCl by 2. Okay, so that then gives us 9.95 times 10 to the minus 4 moles of calcium carbonate. What is the mass then of that calcium carbonate? We use N equals M over Mr. Rearrange that, so therefore M equals N times Mr, and it's the Mr of calcium carbonate. So that's 9.95 times 10 to the minus 4, which we got from here, times by 100.1, which is the Mr of calcium carbonate. And that equals 0.0996 grams. And then the last one, calculate the percentage purity. So to do that, that is our calculated mass, which is this, divided by the average mass used here, times by 100. So 0.0996 divided by 0.1267 multiplied by 100 gives us 78.6% purity. These back titrations do take a lot to think about, because obviously there's two, instead of a normal titration, we've got a straightforward calculation. We have two distinct parts to the calculation that we have to do. So again, we've worked out a purity. It's not 100% pure, okay? So obviously there's 21.4% within that sample that we tested potentially isn't calcium carbonate. So again, we can have a think about that. Where do we think we could? And of course, with that, relating it back to this methodology as to where we could have got impurities. So think about what I started in the video talking about the methodology and issues there, and relate that back to the percentage purity that we've just calculated. Okay, that's calcium carbonate over with. Our next one will be copper oxalate, so look forward to seeing you then.